Good day, one and all. Welcome to the HESA e-library, also called the HESA Video Bank. This is part one of a series of videos that will talk about all these concepts. So all the listed concepts here will be talked about. But then in this particular video, we'll limit ourselves to the origin of elements and atom. Very simple. And so we want to appreciate how far we've come with respect to our knowledge of the atom, right? Good. So we start off with the Big Bang Theory, right? So the Big Bang Theory forms the basis of how the universe came to be, right? It's one of, it's the widely accepted theory about how our universe came to be from science, right? Now, it's the whole concept is a very complicated concept, but then we'll try and then break it down into simple terms for us. So two ideas. Now, the main assumption in current time that makes us believe the Big Bang Theory is that the universe is expanding. Even to date, the universe is still expanding, right? Good. And so it gives an idea, okay, the expansion has been continuous. That's the belief. The expansion has been continuous. Now, the theory says that the whole universe was formed from a singular atom that exploded. Now, the singular atom had infinite temperature. So it had infinite temperature and then infinite density. It had infinite temperature and infinite density. And out of the explosion of this singular atom, we have everything coming into, right? Now we are seeing that from facts, we know that it has been 13.7 billion years since that explosion came into being, right? And so that is just it. We have a singular atom, very, very, very small atom, right? And then exploding, that's the Big Bang, explode. Then the explosion happened in a matter of a fraction of a second, not even up to a second, milliseconds, right? For the whole universe to be created. But then the transition, we appreciate that the transition took time, right? So our universe has not always been there. After the Big Bang, it took about 3 minutes before we got nucleus. 3 minutes is a lot of time. I mean, with respect to this, it took about 3 minutes. So it took about 3 minutes for there to be a billion decrease in temperature. There to be a billion degrees in temperature before we form our helium and then our hydrogen nuclei. And then after that, it took us about 3,000 years, 300,000 years, yes, actually, 300,000 years before the electrons could combine with this nucleus in order to form atoms. And the atoms we are talking about are hydrogen and helium atoms, right? Now, these atoms came together because of gravitation, put them together so that we could get clear, transparent clouds of gas, right? And that is how our universe started. Apart from the Big Bang Theory, we have other theories that explain how everything came into being. We have the fusion theory. Now, the fusion comes from a very simple concept in chemistry, which is fusion reaction. Generally, fusion reaction is when two small nuclei come together to form a larger nuclei. And that is exactly what happens in the star. Right? That is why we call it the stellar hypothesis. The stellar hypothesis. And so we realize that the second point is saying high temperatures and then concentration of reactants are required. They have given us example of them. And the first example is we have 2 moles of helium. 2 moles of helium coming together. Now, these 2 moles of helium will come together to form beryllium, right? And then beryllium will combine with helium again to form carbon. And carbon will combine with helium again to form oxygen. So every other element was formed from helium and hydrogen. Helium itself is also gotten from hydrogen, right? And so that is it. The true fusion reaction, we have been able to produce all the other elements that we have now, right? Now, the next point says that ion. So ion, largest atom formed from nuclear fusion, right? But then he also appreciates that ion can still trap neutron to form other larger atoms, right? So that's for that one. Now, the last point in the stellar hypothesis is elements with even mass numbers are produced by mainstream fusion reaction, whilst elements with odd mass number are produced by side stream fusion reaction. Now, this is a very important concept. I wouldn't go into it, but the truth is, even mass number elements are more stable, right? So fusion reaction will generally lead to more stable product, which are the even mass numbered elements, right? Now, if you have But the examples I give up there, you realize that all of them were leading to even numbered. Let me go up. So let's go up, 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 up. Good. So these ones, right? These ones, you realize that all of them were leading to even mass numbered elements, right? So that these are the mainstream reactions that we are talking about. But the truth is, there can be side reactions like this. Carbon 12 attracted a proton, right, which is hydrogen, now to form carbon 13, right? Now this is a side reaction leading to an odd mass element. Now the truth is, the carbon 12 here, or the even numbered one, generally are more stable than the odd numbered one, and hence they are more predominant. They are more predominant, and the odd numbers one are less predominant. So that is that for the last point when it comes to the stellar hypothesis. Now we are not done. There's another hypothesis that we have to consider, right? That's not all elements are made naturally. There are some which are made in the lab, some which are made in the lab. And so we are seeing that elements with atomic number above 92 have been synthesized in the laboratory, right? Yes. Now we call those elements trans-uranium elements. The truth is all of them are gotten from uranium. So we take uranium, the atomic number of uranium is 92, as we have here, 92, right? And so you take uranium and then you add subatomic particles to it, you bombard them with subatomic particles to give you the other elements that we have, which are above 92. Example has been given, californium. We have a lot of them, americium, plutonium, a lot of them, right? Plutonium, einsteinium, so a lot of them, right? Yes, but let's look at the example. So we have given us californium. Californium is atomic number 98. And they are saying that californium is formed from fusion of the nuclei of carbon 12 with uranium. I said they are called trans-uranium elements because they are gotten from uranium. Very simple, right? Good. So that's for that. Now let's come to an area which is of relevance to us as health personnel. So elements that constitutes the cell, right? So we are saying about 30 elements are recognized as essential to living cell. Selection factors include properties of the biosphere. So there's a very interesting fact to keep. We'll not explain it a lot. They are saying the composition of the earth and its atmosphere compared with human. That elements in the earth are similar to elements in the human body. One. Now they are saying there's similar concentration of main ions in seawater and blood plasma, which is a very interesting fact to note. When it comes to chemical democracy, we are looking at the fact that almost every group has representation in the cell, right? Almost. Now, the almost is because of the next point, which says that 15 out of 18, right, groups have representation. So there are 3 which do not have representation. Now, the whole thing has been broken down by the next point, which says that the F-block elements, do not have representation, right? They do not have representation in the cell. Now, we have noticed that the distribution of elements in the cell are different. Some of them occur in higher quantities, some of them occur in lower quantities. The ones that occur in higher quantities are called major or bulk elements, and the ones that occur in minor quantities are called minor elements, right? Good. So the major ones, they make over 99% of the mass of the cell. Now they are carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Those of us who like using acronyms, we can use this. CHONPS. So these are the first letters of the major elements as listed. The words by we say this is chomps, right? Chomps. Very important to know. So this is a very simple way of getting. Now, by logic, it means that the elements which are not here are minor. But bear in mind that not all elements are found in the body, and that can be the trick, right? Because if you are not major, you should be minor. That's provided you are found in a cell. Good. So that's it. Let's go to the minor ones. Minor ones. Yes, so the minor ones are manganese, iron, cobalt, nickel, right? Yes, now they are saying that they are primarily present in the fluids that beat the cell. Now, features of major elements. mostly they are P block. Now we are using mostly because we know that one major element like hydrogen, right, is in the S block. So very important to note. Now they are able to form covalent compounds. They are non-metals, as we can observe. All of them are non-metals, the major ones. Now they have smaller atomic size and numbers, and then they are neither too reactive or too inert. So they are not unreactive, but they are not too reactive. So that is what we are talking about. Right now, exclusion. The elements that you will not find in a cell, artificial elements, the one above 92. Now, there are still some elements which are below 92 that we cannot find. Technetium, astatine, francium, they are also artificially made, even though they are below 92, and then you cannot find them in the cell, right? So we have inert elements. So the inert one, the unreactive one, the rare gases, helium, neon, argon, xenon. So those ones, they are not. And then the actinides and latinides, they are also not found in the cell, right? Then the next one is talking about toxic nature of elements. So lead can cause anemia by inhibiting heme synthesis. Very important to note as a health professional. Mercury is one of the reasons why we say galamsey is not good, because of the mercury they use in their extraction process. When the mercury contaminates our air, that's the gaseous mercury and our water bodies, it leads to liver, kidney, and brain damage. All these are very significant organs that we cannot do without. That is why it's very important to know as a health to them. Beryllium interferes with many functions of magnesium, which is an important cofactor in the body. We understand the role of magnesium when we do biochemistry. Now, the cell doesn't also have radioactive elements with radioactive nature, like uranium, right? So naturally, our cells do not have some of these. Now, uranium and other radioactive elements can have good or bad effects, right? So we'll talk about them. Yeah. So we say uranium gives off radiation that could harm the cell, even though the radioactive elements are not essential in the cell. It can sometimes provide valuable quality of life to cells, right? So anti-cancer, we can use the platinum complex anti-cancer drug. So we have chemotherapies and then radiography, and then a lot of things that we apply radiations, right, to health. And so even though generally we are saying they are not healthy for the cells and they are not found in the cells, they are very important practices that we need radioactive elements to do in health. Now, we have entered chemistry proper, because this time we are talking about one of the most abundant elements and then most important element when we talk about organic chemistry. When we talk about the chemistry of living organisms or the chemistry of cell, that is carbon, right? Now, carbon has unique properties that makes it be able to form or perform all its function. The first one is that it has an ideal size. It is neither too big nor too small, right? And so it can form stable covalent compounds. Very important to note. Now, the next one is the power of catenation. Now, catenation is gotten from a word called catena, which means chain. So we are looking at the ability of carbon to form chains. Right now, the chain can be straight. The straight chains can be like this: carbon-carbon bond. So carbon to carbon to carbon, right? Yes, straight chain, like propane, right? Straight chain. That's straight chain. Then it can be branch chain like this. So we can have this, right? Yes. So this is, let me count. This is neopentane. This is neopentane, right? So neopentane like this is, if you want the systematic name, it is 2,2-dimethyl propane, right? Yes, so it can also form branch. That's another chain, which is a branch chain. Now it can also form a ring. So we have something like this. So catenation, they can form chain. The chain can be straight, it can be branch, or it can be cyclic or ring, right? So that's another thing that we can look at. Now the next one is that it can form multiple bonds with itself. Now the catenation is with itself. Let's bear in mind. So it can form chains with itself. That's what we are looking at. Now when we come to the next one, it can form multiple chain. It can form multiple bonds with itself and other elements. So it can form something like this: C single bond C. It can form C double bond C, and it can form C triple bond C. It can form C double bond O, right, which is found in groups like carbonyls. It can form C triple bond N, which is formed in groups like cyanides. So that's another property that enables it to perform its functions, right? So multiple bonds. There's a last one that we have to add. Let's quickly run to the last point. Oh, come on. Yeah, so this is the last point, tetravalency. So it can form 4 separate bonds, right? Carbon form 4 bonds, always. Carbon form 4 bonds, right? Yeah, carbon form 4 bonds, unless it's in its ionic or radical state. But then neutral carbon would form 4 bonds. Very important. So these are the unique properties of carbon that makes it be able to form its. Now we need this knowledge so that we can understand organic chemistry. Very important, right? But now let's move on to how far we've come respect to our understanding of matter and the atom. Now, the study about matter started years before Jesus Christ came, 500 BC. Around 500 BC, Democritus suggested that matter is made of particles. So that was the first thing that we thought about. There was no intense study, but we knew that he suggested the particulate nature of matter, right? Call them atoms. Now, Aristotle came to propose, right, that matter was continuous and not composed of small particles. So Aristotle was talking about the wave nature of matter, not particles. So these were two contradicting viewpoints when it comes to matter. He named it Hale. But then if you read better, there were other studies that later combined the fact that an atom or matter can actually behave as a particle and a wave. So now we got the dual state of matter, which was studied by de Broglie. We'll talk about that concept along the line. So that is the best that we have now. But early, the Democritus came to say that matter is made of particles. And then Aristotle disagreed and said matter is made of what? Wave. It's continuous. Good. So these were the two things that came before. Now, an English school teacher, John Dalton, came in. And then he was the first person to give us laws or postulates for it to form basis of research. So the postulates he gave us, even though most of them are disproved now, right? It became the basis for scientists to research on. Good. So he put forward some postulates which we'll talk about the physical and chemical properties of atom. Now, his postulates were based on the laws of definite proportion and then the law of conservation of mass. Now, these were the postulates of John Dalton, the English school teacher. So, John Dalton said, elements are made of small indivisible particles called atoms. Now, the stress word here is that he said they are indivisible. Now, we know that atoms can be divided into subatomic particles, protons, neutrons, and electrons, right? And then even those subatomic particles can be further divided into leptons and quarks. And so that one has been disproved. Now, he said that atoms can neither be created nor destroyed. And now, because of radioactive reactions, we know that we can now create atoms. And that's what we talked about, the artificial synthesis of elements. We can now create atoms and destroy atoms. So now we can create atoms, right? Good. So that one has also been disproved. That's true. Radioactive reactions, nuclear reactions. Now, he also said that atoms of the same elements are identical. They have identical mass and size, same physical properties and chemical properties. Now, because of the concept of isotopy, isotopes, we have elements which have the same atomic number but different mass number. That one has also been disproved. And then his last postulate was atoms combined to form elements in whole number ratio, right? And then this is also arguable, but then it's one of the postulates which still hold water up to today. Good. So I've explained all these the fact that atoms are no longer considered indivisible. Then because of radioactivity and fusion reaction, we can create atoms now. And then the presence of isotopes that challenges the fact that all atoms of the same elements have the same mass number, right? Good. So after John Dalton, many other scientists came in to investigate the property of matter. Some of them were accidental. They were not really looking at the property of matter, but they discovered some properties that could apply to all matter. One of those scientists is J.J. Thomson. J.J. Thomson. Now, J.J. Thomson, this experiment could be said to be accidental discovery because he was looking at studying the property of cathode ray. At the time of his experiment, cathode rays were there. We use cathode rays to make TVs, right? But the behavior of cathode ray, because of different scientific research, was really confusing. So he set out to study the behavior of cathode rays, and that was 1897. Now, let me describe his experiment briefly. We just need to know what he said and then look at his model. We don't have to know every single details. So he took a cathode ray tube. And this is how I'll draw it. This is the cathode ray tube, very simple. Like this. So cathode ray tube. Now the tube here was sucked. The air in the tube was sucked away with a vacuum pump. So the pressure here was very low, right? Left very few gases here, very low pressure, 0.01 Pascal. Very low pressure. So the whole tube had very low pressure. Then he put a cathode here, right? So a cathode here, negatively charged, and then an anode here, and then an anode here, positive charge. At that time, we also knew that the cathodes were negatively charged, right? Negatively charged. It was a knowledge, but it was confirmed through this experiment. And so there was a cathode here, negatively charged, and an anode here, and then he applied a high voltage across it, very high voltage. Now the voltage is around 15,000 volts, very, very high voltage. Now the high voltage caused the cathode to emit cathode rays, which was detected by the fluorescent screen here. The fluorescent screen here was made of zinc sulfide. Now the fluorescent screen was seen as a green glow. So we saw a green glow here, green glow. Good. Now let's look at the investigation that was done. He brought a magnetic field close to this, brought a magnetic field, north-south. Now the rays deflected. Because of the deflection, we realized that then the cathode rays are charged. So that was the conclusion we got from the deflection by the magnetic field. Then he removed the magnetic field and applied an electric field. So the electric field, let's say positive plate here, negative plate here. And he realized that the rays were attracted, were deviated towards the positive. Now, because of our knowledge that unlike poles attract, and then it was attracted in the direction of the positive plate, we knew that the cathodes were negative. So the particles coming were negative. And then he investigated the rays coming, and he realized that it had a constant mass to charge ratio. And the mass to charge ratio of the particles, which are now known to be electrons, is now determined. But we don't need that fact in this video. And then he decided to change the gas in the medium here, the gas which is at very, very low pressure, and the cathode here. No matter the cathode he used, he realized that the same particle with the same behavior was happening. And that made him conclude that then it means the particles coming from the cathode here is a fundamental constituent of all matter. Fundamental. And that led to his model of the atom that he brought. That was the first model of the atom. And then the other scientists built on this model. And he said that the atom is like a plum pudding, which is a food, or watermelon, right? And so it's like this, a sphere, a solid sphere like this, with positive and negative charges evenly distributed. Positive and negative charge. Now, where did he get the concept of positive from? Because his experiment didn't tell us anything about positive. But he knew that most matter or most atoms were neutral. So if he has discovered electrons which are negatively charged, then there should be a positive charge. So he just said that then the atom is a solid sphere, right? So just like you have watermelon with the seeds in it, we have positive and negative charges evenly distributed. And that is the best of J.J. Thomson that we know. The best of J.J. Thomson. Then came his students. Now, mind you, the two next scientists I'm coming to mention are students of J.J. Thomson. And they all won Nobel Prize even before J.J. Thomson, because J.J. Thomson's Nobel Prize came later. But they were all his students. So they came Ernest Rutherford, Lord Ernest Rutherford. And he's my favorite scientist, for the record, my favorite scientist. And because what he did was very smart, if you ask me. Because at that time he was about to do his investigation, he wanted to investigate the plum pudding model, right, of J.J. Thomson to see whether it is true. He wanted to investigate. But then J.J. Thomson had already found the electrons, the negative particles. So it was just wise for him to attack the positive particles. And so this is what he did. A summary of his experiment. He did this. He took iridium, which is radioactive, right? Radioactive. So this is iridium in a lead block. And then it was emitting alpha particles. That time we also knew alpha particles. We knew alpha particles. The alpha particles are positively charged. Alpha particle is helium nucleus. Helium nucleus. So like helium nucleus 2+, positively charged. And then he bombarded a thin gold foil with these alpha particles, right? Bombarded thin gold foil. And then he put a fluorescent screen, which is made of zinc sulfide, at the back. Now, this is what he observed. He observed that most of the alpha particles went through the thin foil undeflected. Most of them went through. Then from this, he concluded that if that is what is happening, then most of the space of the atom is empty space, which is occupied by electrons, which are too light. The electrons are actually too light. Too light to what? To deflect the alpha particles coming in. That is what he said. And then because most of the alpha particles are behaving this way, it means most of the space of the atom, right, is occupied by this. Most of the space is occupied by this. So that is it. Then he realized that very few of the particles were deflected through large angles. Through large angles. Then he knew that alpha particles are positive charge. So if there is deflection, it means there's what? There's a repulsion. And so there should be a positive center here, which is repelling them. And so he said that from this, he said that then the repulsion or the deviation through large angles is as a result of the alpha particles coming very close to the positive centers. And because the positive centers are also positively charged, there's repulsion that caused the deviation of the alpha rays through large angles. And then his last observation was that very, very, very few of the particles were directly bounced back. Very, very few of the particles were directly bounced back. And then he said that from this observation, he knew that these alpha particles had a head-on collision, a direct collision with the nucleus, the positive center. That's brought it back. Because it's a head-on collision and it's positive charge, and it's a dense positive charge, it was able to send the alpha particles back. And then he said, because very, very few of the alpha rays behave like this, it means that the positive and negative centers of the atom is not really distributed like J.J. Thomson said. But the positive centers are in the middle, right? There are very few in the middle. There are very few dense centers in the middle. Very few dense centers. Very few, because very few of the alpha particles were reflected back. So that is what he said. And so from this, he also brought his model of the atom. And then he said, because now he was able to discover the positive center and name its nucleus. So the nucleus had come into being. So he said that then his atom will be like this. An atom would be the solid sphere like this with a positive center, and then it would have electron around it in orbits. Electron around it in orbits. Electron around it in orbits. So that is what he brought. This will still give you the neutral atom that we have. So we accepted this for the time being. But then this concept was against classical physics. Because if it's true that electrons are in these orbits and then they are moving around this positive center, then they should lose energy. There should be a pull from the positive to the negative here, and they should lose energy. And so they should lose energy continuously to a point where these electrons will collapse into the nucleus, and then we'll have to see the whole atom collapsing. And so on a normal day, we should have been observing matter collapsing because of this property. That is, if Lord Enes-Rutherford was correct. And so it was against classical physics. And that is when the next student of J.J. Thomson came in Narbo. Now, Narbo uses knowledge of classical physics to explain the behavior of the orbitals to us. The behavior of the orbitals. So he said that yes, there could be orbitals around the nucleus, but these orbitals are fixed energy states. And so far as electrons are here, the electrons will not lose energy. The electrons will not lose energy. And then electrons, the orbitals are at different distance from the nucleus. And the further they are from the nucleus, we'll talk about the energy they have. And once they are in their energy level, they can move without losing energy. But then they will only gain or lose energy if they want to transition from one energy level to the other. So assuming one wants to move from this energy level to the other, then they need to gain one quantum of energy. And then in order for you to fall to a lower energy level, you need to lose one quantum of energy. And because he defined the orbitals and defined these properties of us, he actually answered some issues that we got from classical physics. Some issues that we got from classical physics. But then the limitation about Narbo was that he considered the atom and then the electrons as particles, which will be in definite orbit, moving in circular orbits. No. But that was to the neglect of Louis de Broglie's idea that the atom, right, is a particle and a wave at the same time. So the wave nature was not considered. And that is when Schrödinger came in. Schrödinger. So this whole thing is like a story, right? So the Schrödinger brought the wave mechanic model, and then he treated the atom more like a wave, right? So he combined the particle nature and then the wave nature. And then he brought an understanding of quantum physics. So whatever Schrödinger did formed the basis of what? Quantum physics. And it is from the Schrödinger model that we came to get we appreciated the Heisenberg's uncertainty principle. Because the Heisenberg uncertainty principle came from the wave nature of the atom. The wave nature, not the particle nature, the wave nature. Let's move on. Let's read something more about. So we've talked about all these people. So the wave mechanistic model of the atom. So I already said that Schrödinger borrowed some concept from Louis de Broglie, which Louis de Broglie's hypothesis, which suggests that the electron has dual property. It has a wave and the particle property, and the electrons can therefore can therefore have both momentum and wavelength. And then Heisenberg uncertainty principle said it will be difficult, right, near to impossible to determine the position and the momentum of electron at the same time. Now Schrödinger brought an equation which, when you solve the equation, you can get the wave function. Now he changed the concept of orbitals to wave function. So instead of the orbitals being circular spaces, he said that no, they are not circular spaces, but they are volume of space. He made everything like a probability. So the orbitals are not circular path around the nucleus, but then they are volumes of space where there's a high probability of finding electrons. And that is the wave function. Right? That's the wave. So his wave function was called orbitals. And then the orbital was a volume of space that's there's a high probability around the nucleus where there's a high probability of finding electrons, about 95% probability of finding electrons, right? So that is everything about how far we came. We have come with respect to the scientists who contributed to the properties or the nature of atom and as far as we can consider matter as we have now. Now, from all that has been said, we got a concept that we use to describe the entire nature of electron and the entire nature of orbitals. And we call that concept quantum numbers, right? And so in the next video, we'll talk about quantum numbers. Talk about quantum numbers and how quantum numbers can give a complete description of electrons and how we can use the knowledge of quantum numbers to write the electronic configuration, right? And how the electronic configuration would now give us an idea about how periodic table has been arranged, right? So that is that for that. Thank you very much. And then I'll see you in the next video.